So in this video, I'm going to go over 3.10, 3.11, and 4.1. The first one on 3.10 is we're looking for the derivative of the inverse of a function at a point. Your book goes over the formula for this, and you have to be very careful with your endpoint and your x point. So here we're looking for the derivative. You're going to plug in a y0 value into the inverse, and you want to find that derivative, and it turns out it's going to be 1 over the derivative of the value you plugged in the original function to get y0. So this is the value you plugged in the original function to get y0. So here we're looking for the derivative of the inverse function of 8. It's going to be 1 over the derivative of the function that I plugged into my original function to get out 8. So what did I plug into my original function to get out 8? I got 6 there. So I'm going to take the derivative of the function at 6. So here would be 2. So my answer would be 1/2. Your book goes over a few different ways on how this was calculated. What you want to ask yourself is, what did I plug into the original function to get out y and y0? The derivative of my original function's inverse at that y0 point is going to be 1 over the derivative of the original function at the x0 point. So here you're given just enough information to come up with the derivative of the inverse of the function at 8 is going to be 1 over the derivative of the original function at 6, because when I plug in 6 to my original function, I get out 8. So I'm going to be plugging 6 into the original function's derivative to get out 1/2 as the derivative of the inverse at 8. So I know it's kind of crazy, but as long as you kind of see this formula, and you don't have to do too much with it. It's a really kind of complicated thing of what's going on here. Generally you have a function, but if you just had points, or you'd be able to talk about the derivative at a point. And it all stems from that if you have a function f of x, the derivative is reflected about the line y equals x. So if you know f of x, then you would know f inverse of x. And you're kind of taking the function reflected about this line y equals x. And so that's why you can look at the slope this way. The next question is going to be a from 311. And you have to come up with a equation relating x and z, and the rope passing through a capstan on a dock is attached to a boat offshore. So the rope is being pulled in at a constant rate of 3 feet per second. The capstone is 4 feet vertically above the water. So we have something like this. We have this boat out here. We have this is 4 feet above the water. We have this rope is being pulled in at 3 feet per second. This is my z, the length of the rope. X is the horizontal distance, and this is a constant of 4. So relating these three terms, are relating x, 4, and z, I have x squared plus 4 squared equals z squared, which is what you got there. Differentiating it with respect to time in this case would be 2x dx over dt plus 0 equals 2z times dz over dt, where dz over dt is given. So we end up with simplifying it. When the boat is 14 feet from the dock, it is traveling about So when this boat is 14 feet from the dock, how fast is it traveling? So here we're going to evaluate when x is 14 feet. We want to calculate dx dt. So find dx over dt. So everything is given here. X is given at 14. dz over dt is given at 3. And actually, we're just given enough information here to find the corresponding z value, right? So if this is 4 and this is 14, what would z be? So 4 squared plus 14 squared, the square root of that. Z is approximately the square root of 212. So I'm just going to leave it as the square root of 212. So z is square root of 212. So I had to go through and find this one extra bit of information. But I want to solve for dx over dt. Dx over dt is going to be divide through by 2. I would have z, which is the square root of 212, times dz dt, which was given as 3, divided by x, which was given as 14. So I have the square root. This is approximately 3.12 feet per second. Is everything in feet and time in seconds? Yeah. So you might have to go that extra step and solve for the missing z value when you're given a specific x, and then plug everything into the equation. Here, find the critical points. We're looking at 4.1. Critical points are when the derivative of the function equals 0 or are undefined. In the domain. So if you talk about the domain of this function here, you cannot take natural log of a negative number, and you can't take natural log of 0. So here x is in the domain 0 to infinity. So we're only going to look at the values that the original function can exist in. So the derivative of the function would be minus x to the minus 2 minus 1 over x. Set that equal to 0. So we already know x cannot equal 0. If I multiply through by, well, just rearranging this, what would I get? I would pull minus 1 minus x equals 0. So x equals minus 1. My only critical point. That's not in the domain, so therefore there are no critical points. So 0 and minus 1 aren't in the domain of the original function. So they can't be a critical point because the graph of that function doesn't exist at that point.